should start. All right. I've been substitute teaching so long, I almost said I'm Lieutenant Colonel Richards, but if you guys don't know that by now, then I can't help you. Quick admin, we're here today, and then Wednesday, or no, today's Wednesday, Friday, and then I just realized that I said that stuff is due on Monday, but I think I'm a liar, right? Because that's actually Tuesday. So yes, I'm sorry. Tuesday is when those things are due, because Tuesday is the next. So that's Tuesday on there. So get those done by then. The other thing is we are going to go over Intro to Chi-Squared today. And then tomorrow, or not tomorrow, Friday, we're going to do more Chi-Squared. And based on what I've gotten through with everyone else today, I assume we will get through enough that Friday should not be too intense. So I am hoping to keep at least half, if not more, of the class for homework and lab questions and working on your own. So with that in mind, I'm just saying to bring what you can on Friday. Questions or lab, and hopefully we can spend some time working on that. All right, any questions on any admin, life, the universe, anything? I guess I actually haven't heard any voice but my own. Shane, can I get a mic check? Do you guys actually hear me?
Yes, sir. We can hear you.
Outstanding. Okay, Shane can hear me. That's good enough. Let's move on then. Okay, so here is what we are looking at today. Well, actually, here's what we were looking at before today, right? This was kind of the general setup of a hypothesis test, right? Where we said, we started off talking about a hypothesis test for a single proportion, right? And that means I had a null hypothesis that I said, hey, I think the proportion is equal to this. And then I had an alternative hypothesis that was either, no, the alternative is that it's not equal to that, or that it's greater than that specifically, or that it's less than that, right? And we took a estimate and ran some numbers, and then we found a p-value to determine whether or not we decided we had enough evidence to reject the null hypothesis, right? So an example of this might be, hey, what's the proportion? We even had in one of the labs, right? We didn't know that we were doing hypothesis at the time, but we were saying, what's the proportion of cadets who have a math major, right? And we were saying, I think the actual example was management. And our null hypothesis was that it was equal to 1/4. And then we took an estimate and did some numbers, and then we decided to reject that null hypothesis, right? But today what we're saying is, what if instead of looking at a single proportion, we were interested in how the entire population is distributed across a set of categories, right? So with the idea of majors, an example of that would be, instead of what proportion of USAFA are math majors, we could ask, is the distribution of all majors at USAFA the same as the distribution of majors in the US? Meaning, like, hey, if I took the entire academy, a certain percentage math, a certain percent are bio, a certain percent are French, and so on, right? Is that distribution the same as the general distribution across all the US population, right? My assumption would be probably not. We're probably more tech heavy than the general population, but maybe I'm wrong, right? And so we could test that hypothesis, but we would need a new type of hypothesis test, right? Because this would be our null and alternative. Our null hypothesis is not, in this case, our null hypothesis is a P equal to a number. It's that the rates of the distribution of majors is the same as the distribution of majors across the US. And the alternative hypothesis is simply that that's not true, right? And so we're going to show how we can test this, and it's the same kind of process, but we just have to use a couple different tools. So before we get into those tools, any questions about what we are trying to set out to investigate, like what our null and alternative hypothesis mean and how they're different than what we were doing before for a single proportion? All right. So to do this, we need to put together a few numbers. And so for every major, and I say category because we're talking about, in this example, we're looking at the distribution of majors, right? But I could just as easily look at the distribution of the USAFA population across other categories. I could look at it as ethnicities, right? If I wanted to say, is the distribution of ethnicities at USAFA the same as the distribution of ethnicities across other colleges, I could do the same thing. I would just be, instead of looking at the different majors, I'd be looking at the different ethnicities. So we're doing major here, but it's for whatever categories you have decided that you're investigating. The first thing is to find the observed count, or in this case, the observed number of cadets, which we calculate by just counting them, right? So this would be, how many math majors do I have? How many English majors do I have? How many French? The actual count of each one. So I need a list of what the actual number is in each of the categories that I'm interested in. The next one is not a whole lot harder to understand, but it's a little harder to calculate, right? So the next one is the expected number of cadets. And what this means in our example is we are comparing it to the distribution of majors in all US colleges, right? And so what this means is, let's say, for example, let's live in a fantasy world where 10% of all college students are math majors. That's not true, I don't think. But let's say that 10% of all US college students are math majors. Well, then if the distribution of majors at USAFA matched the distribution across the US, we would expect to see that 10% of our students are math majors. So the expected number of cadets would be the total number of cadets at USAFA times 10%. If we had 4,000 cadets, then that means I would expect to see 400 of the cadets to be math majors, right? So that's what we mean by the expected number of cadets, and that we have to calculate it for each one. So there's 3 bullet points there, and you can look at them. But basically, at the end, it's saying for each one, the way we're finding the expected is like that last line. We're taking the proportion or the percentage of people in that major in this case, the US that we're comparing it to, and multiplying it by the total number of cadets here. And that will give us the expected number of cadets in that major. Any questions about what the expected number means and how we're calculating it? Okay, next step, we're going to calculate some z-scores. Now, we did z-scores when we were doing the single proportion, right? If my question had just been, hey, is the proportion of math majors at USAFA the same as the proportion of math majors at all US colleges, then I would only need to calculate a single z-score, right? Because that z-score would tell me how far off my estimate is from the assumed value, and I could figure things out from that. But here we're going to do every single major at the same time. So I need to do a z-score for every major. And so we do that in a similar but slightly different way, right? So the numerator for this z-score is going to be the observed number of cadets minus the expected, right? This is similar to the numerator we've seen before. It's basically what I saw minus what I was expecting. That's what our numerator has always been, right? What we got from what we actually saw here at USAFA minus what we were expecting to see. Where the difference comes in a little bit is what we divide by, because normally we divide by the standard error, right? But here we're not actually dividing by the standard error. We're just dividing by the square root of the expected. Now, you don't need to understand why we're doing that. If you just want to memorize that for when we're doing the chi-squared and we're calculating the z-scores, the denominator is the square root of the expected, that's fine. You can get an A in this course and just thinking of it that way. If you want to know more about it, set up a meeting with me. I will make us some coffee and I will explain to you how it is. It's an interesting thing, but you're going to have to either look it up on your own or come to me, because the book is not helpful on this. I had to actually copy it because I thought it was one of the the ballsiest footnotes I'd seen in a textbook. When it introduces this, it has a little 32 next to it on explaining why it's not the standard error. And it says, using some of the rules learned in earlier chapters, we might think that the standard error would be NP times 1 minus P. Yeah, because that's what we've been doing up to this point, where N is the sample size and P is the proportion of the population. This would be correct if we were only looking at one count. However, we're computing many different standardized differences, right? And that's really the gist of where this is coming from, is that we're doing a bunch at the same time. And so that's why this changes. But if you want to know specifically, I can tell you. Because then what the book says is, it can be shown, though not here, that the square root of the count is a better way to standardize the count differences. So the book's basically saying, look, I totally know why, and I could tell you. I just decided I'm not going to tell you, right? Which is just a really smug, passive-aggressive way of the book just, they may have well just shown a picture of them, the book flipping you off in the footnote here, of basically saying, look, I could tell you, but I'm not going to tell you because you don't care. And so anyway, I found that amusing. But if you do want to know, talk to me. But you do not need to understand. You just need to be able to apply it in this situation. Yeah, what do you got for a question over there, Zane?
Sir, if I were to try that on our next lab, how do you think my chances of success would go?
That'd be interesting. I would, if you just said, it could be shown what the answer is, though not here. Yeah, you will probably get a comment of saying, you could get a grade, though not here. And we'll continue down that road.
Yes, sir.
Outstanding. All right. Yeah, I actually, it's sometimes you try that Hail Mary. So I had a friend in college. We were in an advanced math proof class. And I don't know if any of you guys have ever had to write proofs. It's really fun, of writing whole pages, giving a formal proof of why something is true. And this friend of mine, Dan, he was one of the groomsmen at my wedding. But he had a real bad habit of overusing the phrase, obviously. Like anytime he either didn't know how to go from one step to the next, or he was getting lazy, he would just skip like 1 step, 2 step, or 5 steps, and instead just write, and then obviously this next thing is true, right? And he got away with it for a while, but he must have pushed it too far, because some point in the middle of the semester, he showed me a paper he got back where he had skipped like 6 steps by just writing obviously in between them. And the professor wrote to the side, it didn't give him any credit for it, and he wrote to the side, he goes, Dan, it is obvious to me, but I have 2 PhDs. You don't actually have an undergraduate yet, so why don't you explain it a little more? Which he goes, yeah, that's fair. That's fair. I just want to see it. He's like, I just see how long I get away with it. I guess that time is over. Okay, so what we want to do now is we're going to take all of those z-scores and we're going to sum them all up into a single chi-squared, right? Because each of those z-scores is kind of a mini measure of how well our math major proportion matches the national math major proportion, how close our bio major proportion matches the national bio major proportion. But what we care about is overall, are all of our majors distributed in the same way that they are in the US. So what we're going to do is we're going to take all of those individual z-scores for each of the categories, for each of the majors that we did. We're going to square them and we're going to add them all up. And the reason that we square them, among other things, is because some of them may be positive and some of them may be negative, right? If you look at that, how we calculated the z major, the numerator is the observed minus the expected. So if we observe more than we expected, we're going to get a positive z-score. If we observe less than we expected, we're going to get a negative z-score. So we square all of those and add them all up so that we get because we don't care if necessarily if we're under or over. We just care in general, how far away are we from everything, right? So we're going to square them all up and add them all into a single chi-squared. That's what that squiggly X is a chi, Greek letter chi. And we're going to get one number that is a measure of how far or how close our distribution is to the other distribution, right? Because this whole lesson is called the chi-squared goodness of fit, right? Because what we're talking about is our majors are distributed in a certain way. The United States students' majors are distributed in a certain way. And we are asking, is the way the US is distributed a good fit for how USAF is distributed? Our null is that it is, our alternative is that it's not, right? So we have this single chi-squared, and we're going to use the chi-squared in the same way when we did with a z, where we used p-norm to calculate a p-value to see what's the probability that we would get this test statistic. We're going to do the same thing here, but instead of comparing it to a normal distribution with p-norm, we're going to compare it to what's called a chi-squared distribution with p chi sq. I'll show you the code for it. But the point is that this is a function specifically designed to compare all of these at once. For a normal, we have to know what the mean and the standard error is. Chi-squared doesn't have those statistics. The only thing we need to know about the chi-squared to get R to do it is to tell it what's called the degrees of freedom. And again, this is another one of those things where I'm more concerned that you know how to calculate the degrees of freedom, right? So the degrees of freedom is the number of categories you have, in this case, the number of majors, minus 1. That's the degrees of freedom. If that's all you memorize or care about, you could still get an A in this course and be fine. If you want a little more of a mathy explanation, you can think of degrees of freedom of, think of it this way. So let's say at USAFA there was only 4 majors, and I said 20% was in this major, 20% was in this major, and 20% was in this major. Well, there's only 40% left, and there's only 1 major left. So that last major has to have 40%, right? And so there was only 3 degrees of freedom, because after I told you those 3, there was no choice for what this last one had to be equal to, right? So that's where the degrees of freedom are coming from, in a very hand-wavy way. If you want to get deeper into it, then by all means, send me a message. We can talk, and I can give you more specifics. But that's kind of generally where the degrees of freedom and why it is 1 minus the number of categories. Or sorry, reverse that. 1 less than the number of categories we have. And so once we have that degrees of freedom, then we can calculate our p-value, right? And our p-value is always going to be the upper tail, partially because a chi-squared distribution doesn't look like a normal. It's fat on one end and then it skews over. So we're always going to be on the upper. And also because when we were looking at single proportions, like when we were saying, hey, my brother thought I was cheating at risk, we could have different alternative hypotheses, right? We could have one that says, hey, it's less than 1/6, or one it's greater than 1/6, or an alternative that it's simply not equal. And that decided whether we wanted upper tail, lower tail, or 2-tailed. For a chi-squared, our alternative hypothesis is always going to simply be, or for a goodness of fit, our alternative hypothesis is just going to be, it's not a good fit. And so it's always the same alternative hypothesis. And so we are always interested in the upper tail. And so that's why in our calculation here, it's 1 minus, and then instead of p-norm, it's p chi sq for chi-squared. And then we put in the chi-squared statistic that we calculated for the majors up there, where we added everything up, comma, then the one thing we give it is the degrees of freedom, which in this case would be the number of majors minus 1. And that would be our p-value. And then we compare that to whatever our alpha is. If it's smaller than our alpha, then we reject the null hypothesis. If it's bigger than our alpha, we fail to reject the null hypothesis. Okay, I have some code that I want to go through, and then I will give to you guys after class to play with. But before we look at the code, anyone have any questions either about anything you see on the screen here, or just in general, what's the purpose? What is the thing we are trying to investigate or disprove here that we needed something different to be able to do that with?
How do you know what your alpha is again?
Oh, how do you know? You cut off at the beginning there, and I thought you literally said, I know what your alpha is again. I was like, okay, cool. You guessed my number. Congratulations. You sunk my battleship. So we never actually said it here. So if this was a question, it would probably say something like, conduct a goodness of fit test at the alpha equals something level, right? or if it truly didn't, then in the absence of anything else, you can just assume the standard alpha, which is 0.05. So if there truly wasn't anything here, I would just assume that it was 0.05. Avery, what do you got?
Sir, could you please just explain one more time why you want to calculate the upper tail for this?
Sure. So I didn't, and I'll be honest, I really didn't give too much of an explanation. The shorthand wavy explanation is that for a chi-squared goodness of fit, we always do the upper tail. The slightly longer reason is because unlike for the ones we were doing before, right, we sometimes got a positive, sometimes we were looking at the lower tail, sometimes we were looking at the upper tail because we were wondering if it was an under or overestimate. When you look at the chi-squared, I'm pointing at my screen like you guys can see. I'm sorry, I don't have my magical pen today, so I can't draw on the screen. But in that middle box on the right, when we calculate the chi-squared, it is the sum of a bunch of squares of all the z's. So since we square all the z's and sum them up, we are always going to get a positive value here. And that positive value is how far away from the distribution our distribution is. And so because of that, because we square and we're dealing in positives, the way we measure that is purely from the upper tail. There's no concept really of the lower tail or caring about the lower tail like there is with the normal, because the chi-squared statistic, in a best case scenario, the chi-squared is going to be 0, right? If all of our observed is exactly the same as what we expected, then all of our z's would be 0, and we would get a chi-squared of 0, and that's the smallest value we could get. And we want to know anything off from that, even if all of our things are under, then all of our z's are going to be negative, and then we square them all, and we're going to get a big positive number. And so the bigger the positive, the farther we are, and so it's moving up, down that upper tail. And so that's why we always care about the upper tail, because of how this test statistic is built, if that makes sense.
Yes, sir. Thank you.
Kirst, did you have a question, or did I answer it already?
You answered that question, sir. Thank you.
Outstanding. All right, then let's jump over to nope, abort. Doggone it. I have too many windows open. I'm gonna put somebody's eye out. Okay, hold on a second. Give me 1 second. I'm going to close this window because my poor little laptop that could is chugging and doing the best that it can. One of these days, I should just bring in my gaming laptop and just start using that as my use off a computer. A, I wouldn't have any problems, and B, then in between classes, if I got bored, I could play some XCOM. Okay, let me share my screen here. Again, okay. Are you guys, in fact, seeing my R screen now, finally?
Yes, sir.
Yes, sir.
Excellent. Okay. So we're going to, the question I have here is slightly different than what I was asking there. Instead of saying, are cadets distributed across majors the same as students across the US, I am basically asking, are students' home states distributed the same as across states, the same as the population is, right? And so, and just so you guys know, I am not trying to be like xenophobic here. I realize that some of you guys have home states that are, or homes that are not in one of the 50 states, that may be in one of the US territories, or maybe technically you are coming from another country, but this is based on pull from Camus and just looking at the state variable. So I'm not trying to slight any countries. This is, or territories. This is just for the purpose of illustration. And so we're going to use the prepare, check, calculate, conclude, same as we did before, because it's the same general process. We just, what we have to prepare and check and calculate are slightly different, right? So I guess first, before I go on, is there any questions about what it is we are trying to prove? Because before, nothing's going to really make sense if we don't understand. So what is this thing that we are trying to prove, that the states are represented the same way at USAFA as they are in the country? Do you guys understand what we're going for? I'm gonna take that as yes. Okay, so in the prepare, first, we got to identify our null hypothesis always. Here, rather than being something numerical or mathematical, we're saying, hey, the null is that the cadet home state distribution matches the US population distribution, meaning if 10% of the US population is in Alabama, then I'm going to expect that 10% of the USAFA population is from Alabama, right? The alternative hypothesis is simply that that's not true, that the distributions don't match, that the US population distribution is not a good fit for the USAFA cadet home state distribution. Okay, now, like I said here, unlike before, we need some data, so I'm going to import a CSV, right? And I will, when I post this up, I'll post the CSV as well. But all this is just a CSV of saying, hey, for each state, here's the number of cadets from that state, and here is the US population from that state. And I say I did this, I didn't. Captain Forbes actually did the work to go into CAMUS and pull this last year. But I made a few changes and updated it, so I'm going to say that I made this and that it's not plagiarism. So here is the information we're starting with, okay? Now, the next step is we need to, like we said over here, we have to identify our observed count in each category, right? So our categories are states, and so these are my observed counts, right? That's the observed count from Alabama. That's the observed count from Alaska. That's the observed count from Arizona. If I wanted to pull one of those specifically, I could just say, hey, there's the name of my data set, and that's the name of the variable. And if I want Alabama, I just say I want the first one there, right? So if I run this, I get 56, and sure enough, that is the actual observed number of cadets from Alabama. So that is how I would, if I wanted to access the observed number directly, I could do that. And to be clear, I feel like for this chi-squared goodness of fit, it's actually some of the code surrounding it is a little trickier to understand than the actual concept. I feel like this part is not the hard part. This is, so I'm going to spend a little bit more time going over the code and what it means. But if you are a code master and you don't care, then feel free to tune out during this part. Okay, then the next thing I need to do is identify the expected counts, right? And this is the part I need to calculate. So the expected is basically saying, looking at this and saying, hey, according to this, there's 4.9 million people who live in Alabama. I could then sum up this entire column to figure out what is the entire population of the United States. And from that, I could calculate what percentage of the population lives in Alabama. Once I have that number, then I could say, all right, I'm going to add up all of these numbers to figure out what's the total number of cadets at USAFA. And then I could take that percentage of the US population from Alabama, multiply that by the complete USAFA population, and that would tell me here's the number of cadets from Alabama I expected, right? And so the way I'm going to do that is just step at a time, right? I said, well, first I need to know how many people are at USAFA total, so I'm just going to sum that num cadets column and store that in total USAFA, and you can see that's over here on the right, it's 4,061. Then I'm going to say, now I need to know the total US population. Same thing, but I'm just going to sum the US population column. And that is over here about 327 million, right? Now I need to calculate for each state, I need to know what proportion of the US population that state represents, right? And so I'm going to create a new variable called US pop proportion, and I'm going to say that is equal to the population of that state divided by the total U.S. And so that'll give me basically a percentage or a proportion for each state of what proportion of the U.S. that state represents. Then here's the thing. I did all of this basically just so I could get this, right? The number of expected cadets. And so the way I'm going to do that is I'm going to create a new variable for each state saying the number of expected cadets is, I'm going to set that equal to the total USAFA population times what I just calculated as what should be the proportion of that, right? So if I run all of that code and then output my new data set, it looks like this, right? We had that first 3 columns, but now I calculated this column and this column, right? So this column is the one that says that number means, hey, Alabama, the 4.9 million people in Alabama represent about 1.49% of the US population, right? And so then this final column, the number of expected cadets, that's saying, hey, there's 1.49% of the US population lives in Alabama. If the cadets were distributed in the same way that the US population is, then I would expect 1.49% of all USAFA cadets to be from Alabama. And this right here is what 1.49% of all cadets is, 60.79, right? And so what I'm basically saying here is that, hey, I am, this is how many I expect if we were distributed the same way. And then I can look at it and go, yeah, it's actually pretty close, right? I expected there to be a little over 60 cadets, and there are 56 actual cadets from Alabama. So just looking at that one state, it seems like maybe this is reasonable. The expected number of cadets was not too far off from the actual number of cadets from Alabama, right? And so we calculated that for all of them as part of our prepare step. We're not going to use them yet, but we will in a calculator. So any questions about how we calculated these 2 columns and what they represent? Okay, so now we're going to finish off our prepare step. Just like Nestor said, I need to identify my significance level. And just like he said, we weren't given any mandates. It didn't say what it had to be. So in the absence of any of the question telling me, I'm just going to use the standard alpha of 0.05. So I'm just going to set my alpha to 0.05. That is going to be my standard that I have to be below before I decide to reject the null hypothesis. Last thing on my prepare is my degrees of freedom. And the degrees of freedom is just the number of categories minus 1, right? Which you don't really need for this type of problem. I probably don't need code because there's 50 states, 50 minus 1, 49. I'm a big boy. I can do that in my head. But I keep the code just so that if it's harder, I can't. Here I'm just saying, well, every row represents one of my states. And so the degrees of freedom is the number of rows minus 1. There you go. It's 49. We did it. All right. Any questions about anything in the prepare step before we move on to the check step? Okay, so for the check step is going to be a little different, right? Because before when we did check, we checked these, when we were checking sample size, we had to say, we said is NP greater than or equal to 10 and is N times 1 minus P greater than or equal to 10. But that was to make sure that the normal distribution conditions work for the central limit theorem, right? We are now doing a goodness of fit. So N and P don't really make sense here. So we still have to check our size, but we have a new way to check. We're going to say that there are at least 5 expected observations for, in this case, for each state, but in general, for each category. So whatever our categories are, we need to make sure that there are at least 5 expected observations. Basically, we're saying if we were expecting anything less than 5, it's going to be really hard to decide whether or not we are close enough or not, because we were expecting such a small number that if we don't see any, I don't know if that's because we're off or because it was such a small number. So we need at least 5. And this is going to stay the same no matter what. It's always going to be 5. but the important thing is it's 5 for each category. So if we had a much bigger example with many more categories, then this is still going to kind of scale with it because we need 5 in every category. So we need at least 5 expected observations, meaning basically in here, each one of these has to be at least 5, right? So Alaska was cutting it a little close, but it's still bigger. It's 5 or bigger, so Alaska makes the cut. If we want to check all of them, for me, the easiest way is I'm just going to say, hey, look at the number of expected cadets for each state, check if it's greater than or equal to 5, and then count how many times that happens, right? So if I run that, I get 50. Cool. So there's 50 times where the number of expected observations is equal to or greater than 5. I got 50 states or 50 categories, so I'm good, right? If that's still too lazy for you and you want to be cool, you could say, hey, how many times, is that equal to 50? And I could run that and say it's true. Now you don't have to actually count. You can just look at the word and say true. There's a lot of different ways you can code that. Whichever way makes sense to you is fine. But the point is, in this case, we have at least 5 expected observations for every category, so we're good. Any questions about how we do that check step and why it passed in this situation? Awesome. Okay, so we can move on to our calculate. First step, and so now we're on, if we're looking at our slides, we're on the right-hand side now, right? We finished the left-hand side. We know what all of our observed numbers are. We know what all of our expected numbers are. So now we can go onto the right and start calculating our z-scores, right? So we're going to do a z-score for each category, which in this case, each category is a state. So I need a z-score for each state. This is the whole reason we do the prepare step first, because if you did the prepare step, this calculate step is ridiculously easy, right? Because we're just going to say, hey, for every state, the z-score is going to be the observed minus the expected divided by the square root of expected. So I just code that. I'm going to add a new variable for each state saying it's the z-score for that state. And that is literally equal to the number of cadets, which is a variable, minus the number of expected cadets, which is another variable. And then that whole thing divided by the square root of the number of expected. Easy. And that's just going to do it for, since I'm creating a new variable, it's going to do it for every row, which is the state. So I'm going to use a z-score for every state. And if I go to this last line, I can say, hey, just spit out all those z-scores. And sure enough, there are all of my z-scores. Those are my 50 z-scores for each state, right? So each one of those is a measure of how under or overrepresented that state is at the academy, right? That very first z-score right here is negative 0.614, and that is representative as what we saw up here, that Alabama, we expected to see 60, and we actually saw 56. And so that's why the very first one, Alabama, is a slightly negative z-score. That is representing that, hey, actually, Alabama isn't exactly the same represented. It's a little underrepresented. And then all of these are for all of the states. So before we go on to creating our chi-squared, just looking at this as a side question, do you guys see any number in here that seems to stand out to you? $25.75. Yeah, 25. So if you had to guess, what state do you think that is?
California, Texas, or some northeastern state.
Well, so before you think about what it represents, say again.
Wyoming.
Colorado.
Yeah,
That'd be
it actually
Colorado.
ends up being Colorado. I know that because I don't know if they still make you guys do this when you're in elementary school, but when I was in elementary school, they made us memorize a song of the 50 states in alphabetical order, and these are in alphabetical order. So this would be Alabama, Alaska, Arizona, Arkansas, California, Colorado, Connecticut. So that's Colorado, right? And so that big number means, and it's a big positive number, right? Which means, looking back how we calculated it, that means the observed is much higher than the expected, meaning there's far more people, the percentage of people from Colorado at the academy is much higher than what we expected, which means Colorado is overrepresented at the academy, right? Which I have to assume is because of geography, right? We're in Colorado. So there's a lot of people who grew up here, being around the academy, having people who worked at the academy, being interested in it. And so we have and there's just the geographical convenience of if your family lives here, going here. So it is not too surprising that we have a very representation of it. But that doesn't mean we can just say, oh, well, we're done, because our question was not, is the proportion of Coloradans at the academy the same as the proportion of Coloradans in the United States? The question is the distribution among all states equal to the distribution? And maybe, that is not as big a deal as it is, because what we need to do now is calculate the overall chi-squared, right? We're into over here, that middle box on the right here, where we're going to take all those z-scores, square them, and then add them all up into a single chi-squared statistic. So this is my chi-squared statistic, I'm sorry. And I'm going to, for every z-score for each state, I'm going to square it, and I'm going to sum all those up, and I get a chi-squared test statistic of 936, right? Now, just looking at that, I can't tell you if that's good or bad, because it depends on our particular chi-square distribution based on how many degrees of freedom, right? So I can't say whether that's good or bad until I use it to calculate the p-value, which is what we're going to do right here, right? We're doing the upper tail, so it's 1 minus, and then instead of p-norm, p chi-sq, and then the number that we just calculated up there based on the degrees of freedom we did, which is 49. So I run that, and I get 0. So the answer is not 0. The answer is 0.0000000. But at a certain point, R was trying to list out the zeros and then said, wait a second, I'm telling this answer to a human. Humans don't care. It's zeros for all you're concerned. It's so small, I don't want to hurt your brain and tell you how small it is. It's just basically 0. So it's not 0, but it's almost 0. That's our p-value, right? And so with that, we can then do our conclusion. So I get down here, and here's my little part that I just code that says, hey, spits out all of our values that we agreed on. But the overall conclusion is that because our p-value is less than our alpha, not just less, but crazy less, right? Because our alpha was 0.05 and our p-value is essentially 0. That means we have statistically significant evidence to say that the number of cadets from each state, or how cadets are distributed amongst states, does not match how the U.S. population is distributed amongst states, right? So we reject our null hypothesis. Our p-value is less than alpha, so we reject our null hypothesis, and that's what this means, right? To put it another way, if I look at, here's a map that we made of the U.S. population. So there's some things on here. A lot of states are generally more or less the same, but you can see certain states like California. There's a big concentration of population in California. Also, Texas, New York, and Florida kind of come in second as populous places. But that's the general distribution. If I make that same map for cadets' home states, you can see that there are definitely a lot of similarities, but there are some places where it is very different. Colorado, for example, there is a heavier concentration in Colorado at the academy home states than there is for the population. Another thing that stands out to me is if you look at New York on the two, it looks like New York is underrepresented at the academy, right? And maybe Texas, it looks like, is a little overrepresented. And I could try to make, if I really was interested, I could do more research. But if I wanted to make a conjecture about this, I might say, well, maybe that makes sense based on the general kind of political leanings and makeup of the different states. You're probably going to find fewer families who grew up in New York who are interested in sending their children to a military academy, whereas in Texas, you're going to find more people who are interested in sending their children to a military academy, right? So maybe that explains it, maybe that's not. But the point is, what we set out of saying, is the distribution of home states of the academy the same as the distribution of the U.S. population? And our hypothesis, we rejected that, saying, no, there's significant evidence that it's not, because when we got that test statistic, we got a test statistic of 937. This is what a chi-squared, in particular, this chi-squared distribution looks like. And so our statistic was all the way over at 937. And so when we calculated the p-value, we found the upper tail basically saying, if we were the same distribution, what's the probability that we would have gotten a statistic of 937 or higher, right? And it turns out the probability was crazy low. And so that's why we said, no, that's no chance we would have gotten this. The null hypothesis is wrong. We're not distributed the same way. Whereas if all of our z-scores had been 0, meaning the expected and the observed were exactly the same, we would have ended up getting a chi-squared of 0, which, as you can see, would have given us almost 100% probability, which would have been way higher than our alpha. And we say, oh, no, I can't reject it. There's a very good probability that I would have gotten this number. Yeah, sorry, Nestor, I was trying to finish my thought, but you had a question. What's up?
Sir, you just answered it. Thank you.
Excellent. I'm glad to know my ESP is still working. Okay, that is the big general pieces of how to do a chi-squared goodness of fit. And I keep saying goodness of fit because on Friday, we are going to use chi-squared to do another one, right? When we introduced hypothesis test, we use the normal first to say a proportion, and then we use the normal again to do a difference of proportion. So we use the same normal distribution for a single proportion and a difference of proportion. In the same way, today we used a chi-squared to show a goodness of fit to try to do the hypothesis, is one distribution the same as another? On Friday, we're going to use the chi-squared to do another hypothesis test about independence. And if this made sense, Friday should be even easier. If this didn't make sense, then just make sure you read up on it and bring questions or shoot me questions between now and Friday on that. In the meantime, does anyone have any questions or want me to go back to any slides or code of what we were doing today, either conceptually, mathematically, or code-wise? All right. Well, if you guys are truly understanding all this, that is great. There's no reason for you guys to just stick around and practice bleeding. So we got about 5 minutes left. Feel free to take off and get a 5-minute power nap before M4. I will stick around if anyone has any questions. But if I don't see you before Thursday, I will see you on Wednesday. And remember, I'm hoping to use at least half of that class to work on lab or ask questions. So bring stuff that you have and we will go over that. Otherwise, keep working on the lab and the homework, look at the guided lessons, and I will see you on Friday, if not before then.
Thank you, sir.